Roger, today there are many physicists talking about extra dimensions. On a microscopic level, string theorists compactified 5 or 6 dimensions, spatial dimensions. On a large level, these large extra dimension brains, as they're called, are now commonly put into various cosmological schemes. They're all mathematically based. What's your reaction to these extra dimensions?
Well, I'm not an enthusiast. I mean, there's no evidence for them, observationally. That's not really why physicists talk about them. But, I mean, they were from theoretical reasons. I have 2 troubles primarily with these extra dimensions. One of them is a more personal reason, which has to do with twistor theory, which is something I worked on and developed over 40 years ago now. And it was specifically based on the fact that we have 3 space and 1 time dimension. And it's a scheme which gets its power from that fact. And it's particularly works in that number of dimensions and doesn't really work in any other number of space-time dimensions.
That's important. So describe that briefly.
Well, it's an idea where you don't think of the points in space-time. Space-time point, you see, is what we call an event. That is, it has no spatial dimension and no temporal extension. So it's a blip like that. And space-time, if you like, is built out of these points or events. Whereas in twistor theory, you take a different view, and that is that space-time points are secondary, and that the primary objects are much more like rays of light. So you think of a point moving with the speed of light. Now that's only an approximation, because really these entities should have spin to them, and they're like a bit more like photons which spin about their axis, and they can spin right-handed and left-handed. So if you take these into account, the fact that they have energy and they have spin, you can represent these objects by single points in another space, and that's twistor space. Now, it's hard to explain the ideas without doing a bit of mathematics, but basically the idea is that space-time points are secondary objects, and you can think of if you like, you want to describe a space-time point, you think of all the light rays through it. So it's like one moment you're looking out at the sky and you see stars all over the place, and each one of those stars has a history of a light ray coming into your eye, you see. So that entire light ray is represented by a single point in twistor space. Now, the fact that it's got a twist to it has to do with the spin of the photon, but let's not go into that too much. But let me mention one point, which is a motivational ingredient, which is perhaps hard to see why it should be unless you have a certain background in physics. But let me try and explain the idea. See, when you look at the sky, you see a sphere, at least, okay, there's the ground down there. Imagine yourself out in space. If there's a sphere out there. So that the different light rays constitute the different points on this sphere. Now, if you had 2 observers looking out at the same sky, moving at very high speed with respect to each other, I see the sky, and I can map this on my sky globe. Well, you see the globes here. Mark it on the sky globe in a particular way. If another observer whizzes past nearly the speed of light and looking out at the same sky, that globe will be distorted. The map they see will be squashed in one direction and stretched in another direction. Okay, well that's an effect called stellar aberration, which is well known since Bradley first saw the stars slightly displaced as the Earth went around the sun. But the thing is, in relativity, this particular transformation of the sky globe is one which is what's called conformal. That is, it preserves angles. Now, the key point here is that there's a very nice mathematical way of describing the transformations which have this property. And this nice mathematical way uses complex numbers. So you use the square root of -1. And the transformations are exactly the ones that you would use if you thought of that celestial sphere as what's called a Riemann sphere. That means all the complex numbers folded up with infinity. You have another number, and it makes a sphere. Okay, mathematicians know all about these things, but they're not so familiar to people who aren't mathematicians. But the idea is that this is a complex thing. It uses the square root of -1. Now, why is that important? It's important because of quantum mechanics. The theory of quantum mechanics tells us that when you talk about small things, you have to use these complex numbers. And when you talk about how things can spin, they can spin in different directions. And these spin directions are built up from two opposite directions. You can choose whichever two you like by the use of these complex numbers. And the complex numbers spread those two directions into the whole sphere. Now, this again is the same kind of sphere as that I'm using to describe the celestial sphere. So it's in some sense relating the large space of relativity, or that's this complex celestial sphere, to the sphere of quantum mechanics. Oh. And it's making a link between the physics of the small, which is quantum mechanics, and the physics of the large, which is relativity. Which is
the great problem of the 20th century and continues to be the great problem.
That's right. Well, this is a particular angle on that. You see, it's quite different from what most people do who do quantum gravity, that's just trying to make this link. They say, all right, well, quantum mechanics has to be applied to space-time structure. Okay, it's hard to do because it means space-time structure may be granular, all sorts of funny things, you see. But what they don't say is that quantum mechanics needs to be monkeyed with. They say, take quantum mechanics as it is, and it's got to be applied to our ideas of space-time. Now, my view is that that is not correct, that we want a much more even-handed marriage, where quantum mechanics has to give as much as space-time structure has to give. And this means that you don't use quantum mechanics as it exists at all levels. You have to think of the right theory, which is a molding of these two separate theories into one scheme. And for this, one tries to find links between the small and the large, and the link is through this complex number structure. And there are other reasons for thinking that that's a good thing to do, which has to do with solutions of the Einstein equations and all sorts of technical things which have to do with complex numbers.
Fascinating. All right, let's take that
yes.
and now go back to extra dimensions. You said there were two reasons why you are not a fan of extra dimensions.
That's right. Well, one of them was this, you see, because I have to abandon this whole scheme, you see, basically. It's not quite true. There's a certain irony there, which I can come to in a minute if you like. But the other side of it is I just don't think these extra dimensions are stable. They're likely to be, there's a reason for believing they're not stable. When I say not stable, they will just collapse. And the people who hold to the extra dimension view have an argument which has to do with quantum mechanics to say that you somehow can't excite the extra degrees of freedom, of which I see that there are huge numbers of these extra. When you add extra dimensions, it completely swamps the degrees of freedom you had before. And that happens automatically. And you've got to have a real good reason for thinking that that's not going to kill you, you see, in your theory. And the reasons that have been put forward seem to me to be totally inadequate. And I think there are good reasons to believe that these extra dimensions are just not stable, that they'll collapse.
And that's either small or large extra dimensions?
Well, the small ones do it much faster, which is much worse, you see. The large ones, yes, they're bad, both of them are bad. The larger ones are, in a sense, much more obviously bad, because then all the extra degrees of freedom are simply there and staring you in the face. And there's no reason why they're not there. Whereas the small dimensions, you can imagine these quantum mechanical arguments getting around them. And I have reasons to believe, which I put in my book, to argue why the quantum mechanical arguments don't stop them from collapsing. I think they're unstable. So I don't think they're there, you see.
So the dimensions we have are the three spatial dimensions that we know,
and the one time. Yes. Now the irony is that late in 2003, Ed Witten, who is one of the key proponents of
string
theory and extra dimensions, and who has produced an enormous number of wonderful ideas which have had great impact on mathematics, he'd known about twistor theory for a long time. And he then brought some string theory ideas into twistor theory and have sort of brought it back to life in a way which it hadn't been for a long time. So, in fact, it also relates twistor theory to high energy physics, and it has some relevance to the new LHC, Large Hadron Collider, which is presumably going to be working before too long. And there are all sorts of things that one needs to know about the scatterings of gluons. These are the particles which describe the forces, the nuclear forces. And the twistor theory, in conjunction with string theory ideas, seems to provide quite new calculational techniques, which may, in fact, be the basis for some new theory which will enable us to probe more deeply into the workings of nature. However, this would be a version of string theory which does not use extra dimensions. And what's interesting to me here is that maybe these string theory ideas can have a value in theories which don't require extra spatial dimensions. And this would give them, to me, a lot of extra plausibility.